Hello, good people. Welcome to this episode. I'm very excited about this video because in this episode, we are going to take a detour, and instead of the usual theory and hands on sessions we have with deep learning, I figured maybe it's time for us to build something end to end that has real world application. And so, like you can see today, we are going to work on an autocorrect system. And this is largely inspired by the work done by Peter Novick, who is a godfather of AI. He's American, and he came up with a very simple algorithm that can help us to build an autocorrect system. So before we get started, if you haven't already subscribed to my channel, I plead with you to subscribe and also share with your friends so that my little contributions can have far-reaching effect. And you can also click on the notification button to get notified anytime I release a new video. That said, so we are going to focus on building an autocorrect system, and I believe we have all used autocorrect systems before, and we actually use it several times in a day without even realizing that we use them. And even if we know we've been using autocorrect system, I am sure most of us have not spent time to think of how the autocorrect systems that we interact with every day actually work, or how they are implemented. An example is if I go to Google and I spell, let's say, America, I spell it wrongly. Okay, so it turns out that America is something that exists. I want to spell something wrongly. Let's test spelling. I'm going to miss out one L. So I missed out one L in my actual test that I typed into Google, but you can see that Google said, "Did you mean spelling?" So the question is, how did Google know that I typed spelling? How did he know that it was wrong? And how did he know that the correct spelling is actually spelling? So that is what we are going to work on today. I'm going to show you how to build this system from a body of text that should be able to detect wrongly spelled words and suggest the correct spellings for them. And the good news about today's session is that we are not really going to do any of the magic we've been doing with deep learning. All you need to know to benefit from this video is basic Python, and I'm also going to use list and dictionary comprehensions in Python a lot to prevent myself from having to write a lot of for statement or loop statement. And we're also going to do some basic statistic, very basic statistic. If you know how to calculate the probability of an event, then you are okay with today's session. And the last prerequisite is you should know NumPy, which I believe everybody who has followed my tutorials up to this point in time knows about. So let's get started. All right, so to help and make the experience better, I have prepared this note to guide myself so that I know the specific order in which to teach you. And do not assume that because you are not seeing code here, we are not going to write code. I have written these notes to explain to you the steps needed, but we will actually write code to implement every step up until the point where we have a full-featured autocorrect system that uses a probabilistic model to suggest the correct spellings of misspelled words. So, what is the work of an autocorrect system? An autocorrect system basically changes a misspelled word into the correct spelling. And the steps that we have to follow if we want to implement an autocorrect system, according to what Peter Novick did, are: one, we need to identify the misspelled word. How do we even let our model know that? How do we let our autocorrect system know that a particular word is misspelled? I'm going to explain to you how we get to know that a particular word is misspelled. Once we know the misspelled word or words, what we do is we find strings that are n edit distances away from a misspelled word. So another question that arises is, what is an edit distance? What is the edit distance between two words? Basically, the edit distance between two words are the editing operations that must be performed on one word to turn it into the other word. Okay, so if I want to turn the word hot, like what, WHAT, into the word wheat, the grain wheat, what is WAHT? Wheat is WHEAT. So the edit distance between them is actually 1 because I just need to insert an E between W, H, and the rest so that I can turn what into width. So basically the edit operations that you need to perform on one word to transform it into another word is known as the edit distance between those two words. Okay, now there are a lot of edit operations which I'm going to explain to you, so relax for now. The third step is we filter suggested candidates to retain only the ones found in a vocabulary. This is also a mouthful, but basically what happens is once we've identified a misspelled word, we will do some edit operations to generate different words that are similar to the misspelled word. And because of how we generate the candidate words, not every word in the candidate words is actually a valid word. And so we need to filter out. And the way we know that any of the candidate word is correct, I'm also going to explain that to you. It is similar to how we identify misspelled words. Now, having filtered out our suggested candidates, the next thing for us to do is to order the filtered candidate based on word probabilities. So the question is, how do we even calculate word probabilities? We calculate word probabilities from the corpus of tests that we are using to build our autocorrect system. The autocorrect system needs a large body of tests for it to learn from. Otherwise, we are writing code and the code doesn't know anything about correct spellings of words and all those things. So we actually need to give it a large body of tests which are freely available. Like I am using one that I downloaded from the internet, Project Gutenberg. You can download any of Shakespeare's poems out there. You just need a large body of text. You can even scrape some Wikipedia pages. But mind you, the theme of the corpus that you use will also affect the type of words that your autocorrect can deal with. For example, if I build an autocorrect based on a body of text that I got from biology, then I shouldn't expect it to do well when I try to use it on a body of text that is coming from physics, because there will be some words that it has never seen before, like it is not in its vocabulary, but we'll get into the details. So we need to order the filtered candidate based on word probabilities, and a word's probability is basically how likely is a word to appear as far as the corpus that we are using to build autocorrect is concerned. The next and the last thing we do is we choose the most likely candidate to replace. And so because this is probabilistic, we are not always going to suggest the correct word. Mind you, the words that the autocorrect knows is based on the vocabulary set or the corpus of text that you use to train it. So if I'm typing something that it has never seen before, then it will not be able to work with it. So the way to improve the accuracy of this autocorrect system is actually to give it a very large and diverse body of text for you to learn from, and it should be able to work correctly. By the end of this session, you will have implemented it, and it will amaze you how simple it is to do and how well it works. Okay, so the first thing is, now I'm going to go into details for all of these 5 steps and then we start the implementation. So the first thing is identifying a misspelled word. How do we know that a word is misspelled? As far as the implementation of this autocorrect is concerned, a word is misspelled if it is not found in the vocabulary. Let me correct myself. So you see, already we have a place where we can use our autocorrect. So a word is misspelled if it is not found in the vocabulary of the corpus of text that autocorrect system is working with. So let's say my autocorrect knows only I am good. If I type bad, the autocorrect will consider bad as a misspelled word because it has never seen it before. That is how the autocorrect will know that this word is misspelled. Okay, and this is why it is important for you to make sure that the body of text you are using to build your autocorrect system is large enough and is diverse enough so that it has seen a lot of different words out there. Great. Now the next thing is, how do we find a string that are n distances away from the misspelled word? And like I said, we perform editing operations on the misspelled word. And what is an editing operation? An editing operation, is an operation performed on a string to change it into another string. An edit distance is a count of the number of operations performed on a word to edit it. I have explained these. The types of edit operations, we have insert, which is to add a letter. For example, if I have the word to, which is to, and I add p at the end, it forms top. If I insert w between t and o, it becomes to. So the insert operation helps us to transform one word into other words, okay? We also have the delete operation, which is basically to remove a letter. For example, if I have the word hat, I can remove the H to make it at. I can remove the T to make it ha. I can remove the A to make it HT, which is not a valid word in any sense, but it's still the result of the delete operation. So this is why I mentioned that the edit operations do not always return correct words. That is why we need to filter the candidate that comes out of the edit operation. The next operation that we can also perform is swap. So to swap basically means to interchange two adjacent letters. For example, if I have the word ETA, which is sometimes is the abbreviation for estimated time of arrival. It is not a word, is an abbreviation. I can move the E and the T, I can swap them and it becomes tea, like the tea that we drink. I can also swap the T and the A, and the same ETA becomes eat. So there is a swap editing operation that also generates new words from existing ones. The next one is a replace, which changes one letter to another. So for example, if I have the word jar, I can change the W to R and it becomes jar. I can also change the J to a P and it becomes par. Okay, so these are the four basic editing operations that we will be dealing with, and we will write code to implement all of these. One more thing I need you to take into account as far as this implementation is concerned is that the autocorrect has no contextual understanding of the sentences or the words that it will be correcting. If we want to build something like that, then we need to deal with word embeddings, which is something we talk about maybe in the distant future. But for now, we will build something that will be able to suggest corrections for misspelled words, and it works pretty well. Okay, so the next thing is calculating word probabilities. The probability of a word is calculated based on the following formula. So the probability of a word is basically the count of how many times it appears divided by the total number of words in our vocabulary. So if I talk of a vocabulary, it's just all the words that you can find in the corpus of text we are training with. That is as simple as it is. There's nothing complex about that. So if you take the English dictionary, every word in the dictionary is part of the English vocabulary. That is all. So the bigger your body of text, which is also known as the corpus, the better and the more richer your vocabulary is. That is why even in real life, if you want to speak English very well, then you need to have a larger set of vocabulary. If you know just few English words, you struggle to express yourself, or you are not able to express yourself in a way that you always want. So the more words you know about a language, the better your vocabulary is and the better you're able to express yourself. So the probability of a word is basically how many times that word appears in the corpus divided by the number of words in the corpus. So if let's say the word boy appears 10 times and all the number of words in my vocabulary is 5,000, then the probability of the word boy is 10 divided by 5,000. This is all the mathematics you need to know to be able to implement this. Okay, so now we've talked about minimum edit distance, and you know what it is. It is the least number of edits needed to transform one string into another. Where do we apply the minimum edit distance metric? You use it in spelling correction. That is what we are going to do today. And you can also use it to measure document similarity. Like you have two documents and you want to have a measure of how similar those two test documents are. And even nicer application of this is author identification. Like if you find a body of text somewhere and you don't know who wrote that text, but you have a system that is able to tell you, you have a collection of documents that are written by some authors, you can runs some algorithm that measures how similar this new body of text is to any collection of body of text you already know, and it will give you an idea of who could possibly have written that. And that has great applications in real life, because people come across writings and they don't know who was responsible for that. So that is it. And we can also use it for machine translation, like when you want to translate words from one language to the other. These are all things we'll be talking about in the future. And you can also apply minimum edit distance in DNA sequence. And this is biology, is not really my field, so I'm going to leave that for now. So with all the theory gone, it is time for us to start getting our hands dirty and implement the autocorrect that we want to build. So get yourself ready and let's start. So I'm going to start by importing things that I need. And I'm also going to mention that it is really, really, really important that you know about list comprehensions in Python, list comprehension and dictionary comprehension, because I'm going to use that a lot. So if you don't know anything about it, if you know something is okay, but if you don't know anything about it, then I would advise you to pause here and look for a tutorial online about list comprehensions in Python. And once you have grasped the understanding and the beauty of list comprehensions, come back and continue this video and let's build an autocorrect together. So I'm going to start by importing the modules that I'm going to use. I'm going to use the regular expressions modules. I'm going to use the string module. I'm going to use a counter from collections. So I'm going to import counter, and I'm also going to use the almighty numpy as np. Great. So whilst I'm waiting for Jupyter Notebooks to finish whatever it is doing, I'm going to show you the couples of tests we are going to use. I have two test files here. I have big.txt and then shakespeare.txt. If I open the Shakespeare, this is basically just one of the writings of Shakespeare. You just need a body of text so that your autocorrect system can learn a lot of words and their correct spelling. So you are actually betting on the fact that the body of text has words that are correctly spelled. If any word is misspelled in the body of text, your autocorrect system is going to think of it as that is the correct spelling and it won't do anything about it. So as you can see, this is just Shakespeare's writing, and you can find a lot of such writings online as test files. So I have this one here, and I also have one that I got from Project Gutenberg, which is also an open source collection of couples that we can use for things like this. And I'm going to use this big.txt because I feel it's bigger and it contains a lot more words, so it will help improve the accuracy of our autocorrect that we are building. Okay, so in Jupyter, I'm going to use this file, so I have to upload it. So I right click and I click upload, and I come and select my big.txt. One thing you need to note is that yes, it is reminding you. This is what I was going to say. So it says uploaded files will get deleted when the runtime is recycled. So you should know when you close your Jupyter notebook and you start it afresh, the file that you uploaded is not going to be there. So anytime you are playing with this notebook, make sure that you have uploaded your own TXT file, and make sure you also change the name of the file where I use the file name in the code, and that should be fine. Otherwise, it will complain about a file not found, blah blah blah. So that is it. I'm waiting for Jupyter to finish uploading my big.txt. Whilst it is uploading, I am going to write code to read in all the words in the test file. Okay, I just want all the words, because if I do this, you can see that these are sentences. These are sentences, something like this header should be the first thing seen, blah blah blah. And you can also see, to Sherlock Holmes, she's always the woman. I have seldom, blah blah blah. These are all words, so I want to have all the words in this test file. That is what I want to start with, and that is going to form the vocabulary set of our autocorrect implementation. Okay, so I think it has finished uploading. Now I'm going to create a function called read corpus, and you have to pass it a file name. Okay, and so if I come here, what I'm going to do is I'm going to use a context to open the file for reading. So I'll say file name, and I'm going to open it for reading. as file, and I'll say lines is equal to file dot read lines. So I'm going to read all the lines in the test file. And then I have my words list initialized to an empty list, and I'm going to write a for loop here. In fact, I can also use list comprehension to do this, but I'm going to go easy up until the point where I really need to use list comprehension, so that you can also understand if you don't know list comprehension. So for each line in my lines that I have read, I'm going to say words plus is equal to re.findAll. So what I'm doing with this re.findAll is I'm using regular expressions to pass every line and then break it into words, okay? Because if I have a sentence, let me go back here and open this. If I have a sentence, please, let's say, welcome to the world of free plain vanilla electronic test. I want to break it down into welcome to the world. Like, I'm interested in the words, I'm not interested in the sentences. So the regular expression I'm writing here is going to help me to get all the words. And one important thing you want to do is convert all your words to lowercase. So each line I'm going to convert it to a lowercase. It is good that you stick with one case, and we usually use lowercase. Otherwise, if you spell one word in lowercase and you spell it when you are using your autocorrect, you give it something in uppercase, it is not going to see it because it will not exist in the vocabulary set. Okay, so I look through and I add every word to my words list, and I'm going to return words. Okay, so now we have our read corpus written. And we also have our file uploaded. It's called big.txt. So let's see if we can call this function to read our words for us. So I'm going to say words is equal to read corpus, and I'm going to pass in the file big.txt. So mind you, if you are using this notebook and you upload your own test file, make sure you change the file name to match what you have written in how you have named your test file. So I'm going to print something here. I want to see how many words are in there. So I'll say there are, I'm using f strings here, so I'll say there are len words, total words in the corpus. So let's see how many words we got. Okay, so we have about 1.1 million total words, average, like approximately 1.1 million words in there. It is not very large, but it is good enough for what we want to do. And this is not even the most important thing. It is the number of unique words, because you can see that the word like something like that will be repeated a lot of time. Is, I'm good, like they will be repeated a lot of times. So we are interested in the unique words out there, and the unique words in our corpus is what becomes our vocabulary. So let's go ahead and then create our vocabulary. Okay, so we say vocabs is equal to, just convert your words into a set, Python set, because a set cannot a set does not permit you to put in multiple items that are the same. It is actually just going to make sure that only the unique words are going to be in there. So a set only stores unique items. You can't put, let's say, a 5 times into a Python set. It will ignore all the 4 and just put it once. Okay, so we just convert our words into vocabs, and now we can see the unique number of words in there. So I'm going to say print, and then I'll say there are len, and I'm going to say we are going to get the length of our vocabs. So we are going to get the length of our vocabs and say unique words in the vocabulary. Okay, so let's see how many unique words we have in there. I didn't spell vocabs well, so let's get rid of the D. And you can see that we have 32,198 unique words. So you can imagine how many times each of the words are repeated averagely, like from 32,000 all the way to 1.1 million. So you can see that some words or almost all the words are repeated several times, and the vocabs is what we are interested in. That is what the autocorrect system is going to work with. Okay. All right, so now let's do something. We want to know how many times each word appears in our corpus. Okay, we want to know how many times each word appears in our corpus, because it is from this that we are going to build the word probabilities that we will use to select the suggested candidates to fix misspelled words. And that is why we have this counter data structure over here. The counter is just like a dictionary, but what it does is you give it a list of items and it is going to form a dictionary where the items are the keys and their frequencies are the values in the dictionary. So let's come here and I'm going to say words count. So words count is equal to counter, and then we put words over here. Okay, that is it. And then let's try to see how many times the word love appears in our corpus. So I say print, and I mean the body of text I'm using is a story about Sherlock Holmes. So you can imagine how many times the word love will be in there. Word counts is not defined. I didn't spell. Okay, so I said words count and then I'm using word count. Okay, so let's make it word count. Okay, so you can see that the word love appears in our corpus of text 488 times. Let's see how many times the word there appears. And as you can imagine, it is repeated 79,000. I mean, it's not surprising. Let's see, Sherlock, if I spelled it correctly. Yeah, so it's talking about Sherlock Holmes, and so we have Sherlock being repeated 101 times. So these are all preparatory steps that we are doing. At the end of the video, I will actually implement it like I've always done in a correct object-oriented manner with you. But for now, for the sake of understanding, I'm doing everything step by step, and then we'll call all these functions that we are defining to implement the actual autocorrect, end-to-end autocorrect thing. Okay. All right, so now we have to calculate our word probabilities, and to be able to calculate the word probabilities, we first of all need to know the total number of words in there. I mean, we know it from here. It is 1.1 million, like approximately 1.1 million, but we will still write code to do that. Now, like I said, the counter here is a dictionary which has the words as the keys and the word frequencies as the values. So if you want to know the total number of words, we just need to sum all the values in our counter, and that is going to give us the same number here. We can actually do this, but I don't want to hard code. I don't want to use this hard coded number, because if you change the file, which you will when you're playing with this notebook, then the number ceases to be valid anymore. Okay, so let's write code to do that. So I'll say total word count is equal to, I'm going to do something here. I'm going to convert it to a float, and I will explain why. Because we'll be dividing to, like we will be doing division to calculate the probabilities. And in Python, if you divide two integers and you are not careful, it will not do floating point division. So it will truncate the floating point aspect of it, and your division will be wrong. So you need to divide an integer with a float to get something that is not integer division. Okay, so I'm going to say word counts dot values. So I'm just going to sum all the frequencies of all the numbers in our word count, and that is going to give me the total word count. And now I'm going to use dictionary comprehension to create our word probabilities. So I'll say word probabilities, I'll call it word probas, is equal to, I'll say word, and then so a word is mapping to word count for that word divided by total word count for word in word count dot keys. So I don't want to spend time explaining dictionary comprehension and list comprehensions to you, but this is replacing a for loop that I'll have to write to go over the word count dictionary and then calculate the word probability for each word. But Python has this dictionary comprehension, which I really suggest you pause this video if you don't know anything about dictionary or list comprehension and go and learn about it before you continue, because I'll be using this construct a lot. I don't want to write for loops. So basically I'm saying for every word in word count, get that word's word count divided by the total word count, which is the probability of the word, and then put it into a dictionary. This dictionary is word probers, and so it's going to have, each word is going to have its probability. So now we have our word probers calculated for us. Let's see how many times, what's the probability of the word Sherlock appearing. Okay, so I'll say print word probers and I'll give it Sherlock. So what's the probability of seeing Sherlock in the body of text, the corpus, which is basically the text contained in the text file that we are using, and it's telling me that it is 0.000000905 blah blah blah. So it has a small probability compared to some other words. For example, if we check the word probability for de, okay, because we saw that the word there repeats over 79,000 times. So let's also check for the word probability for de, and you can see that the word probability for de is actually much larger than the word probability for Sherlock. So what this means is that if the autocorrect thinks that the is the correct spelling, and it also thinks that Sherlock is the correct spelling, it will put the at the top because the probability of seeing that word in the corpus is higher than the others. We will get to that place. Okay, so the next thing we want to do is we want to come and we are going to start implementing all these editing operations that are needed to implement an autocorrect. Okay, and the first thing that we want to do is to be able to split a word into two components. It might be hard to explain, but I'll write a code and then you see what I'm basically doing. So I'm going to write a function called split. It will take a word, and what it's going to do is it's going to return, and again I'm using list comprehensions here. So it's going to return the word all the way to I, and this is returning a list of tuples, and then the word I to the end, and then for I in range, len of word plus 1. Okay, seeing is believing. It will be hard for me to explain this, but then I'm going to run it and then you see what it's doing. So I'm going to call print split. I'm going to split the word, let's say trash. What do we see here? You can see that the split function is basically returning the word you gave to it as a list of tuples containing two components that put together is going to form that word. Okay, so it starts by saying the first in the first tuple, which is this, the left component is empty and the right is trash. The next, it pulls the T and it puts rush in the right. So you can see that if I put these two together, I still get trash. TR plus ASH is trash. TRA plus SH is trash. Everything here is trash, split into two components. And the reason we need to split a word into two components is because of the edit operations that we will be implementing. So you can see that we have insert, and insert says add a letter. Where are you going to add the letter? Delete says remove a letter. Where are you going to remove? Swap says swap to adjacent. How are you going to do that? Replace changes one letter. How are you going to do that? It starts off by us splitting the word into its component, two components, the left and the right. And this here is just a list comprehension that is looping over the sequence of characters in the word and is splitting it in the manner that I want over here. Okay. So now that we have implemented split, we are going to use split in every one of the edit operations. Let's start off by implementing delete. So we have delete, and the delete operation basically takes a word and it deletes. Let's go up here and see the definition. Let me put this here and then let's come here. So the delete says remove a letter. Okay, so how do we implement something that removes a letter from what split provides for us? Okay, so I'm going to use list comprehension here again, and this is why I said you need to know about list comprehension, because if you don't know, no matter how much I explain to you, you will not appreciate it. So please spend some time and learn about list and dictionary comprehensions. Okay. All right. So I have the delete operation implemented. Let's print delete and let's give it trash. So this is basically going to take trash. Let's see. So it's basically going to take trash and it will return some other, I mean, they are not always going to be valid words. As you can see, maybe it's only rush here that is a correct word. But then it starts off by removing the T, so it becomes rush. It removes the R, it becomes tash. It removes the A, it becomes something we don't know about. We get tra and tras. And that is what this list comprehension app here is doing. If you understand list comprehension, you will not be surprised that it is producing this. So basically, I call split, the function we defined up here, I call it so that I will obtain these tuples of left and right component, and then I use the left and right component to implement whatever edit operation I'm doing. So now I have the delete operation implemented for me, and as you can see, it is generating some things that are not valid words, and that is why we need to filter candidate, because all these things are going to be suggested by the autocorrect, but then after filtering we will only include words that are actually valid as far as the vocabulary of the autocorrect is concerned. Now let's go ahead and implement the next one is what? Swap. Okay, so we have insert, delete, swap. Oh, I started off with delete and swap, so maybe insert will come later. Okay, so delete and let's implement swap. All right, so it takes the word and it's going to return left plus the right, which is the first character in the right, plus the second character in the right plus the first character plus everything after the third character, and then we say for L R in split. So once again we are calling split on the word if and only if the right has a length that is greater than 1. So let's print swap. Let's swap on trash. Swap on trash. So if I swap on trash, you can see that it takes T and R and it swaps them. So I get R tash. And then it swaps R and A. So I get tash. Then it swaps the next two adjacent characters. And as you can see, not everything in here also is a valid word. But the thing is probabilistic. The way the autocorrect works is probabilistic. It needs to do all these edit operations, and when it finishes, it will check for ones that are valid in the vocabulary, and it will use the word probabilities to suggest them. Okay, great. Now let's come here and implement replace. Okay, so def replace word. What does replace do? Let me do this and let's see what replace does. So replace changes one letter to another. So basically to take a letter and then go through all the characters in the English alphabet and it will swap that letter with the English alphabet. And to get all the English alphabet in Python, what we do is we call string.ascii.lowercase. Okay, so I'm going to say letters. So I just want the English letters. So I'll say string.ascii letters and I want it in lowercase. All right, that is why we imported a string module, and this is going to return L plus C. So basically it's doing a concatenation of starting from 1 to the end for the R component, which is right, and then LR in split word if R, so if there is a right component at all, for C in letters. And once again, it's hard to explain this until you see it work. So let's print replace for trash. Sorry, I didn't call replace on it. So replace trash. And then we can see that we have arash, brash, crash, drash, irash, frash, grash, hash, irash, drash, crash, rash, mrash, nrash, orash, frash. I'm having fun here, but basically what it's doing is it is taking every character, like first of all with a T, and it will replace it with every character in the English alphabet. Then it will come to the R, then to come to the A, then to come to the S, then to come to the H. So basically this is a long string of gibberish, but coincidentally you will find some correct words in there, like see crash. This is a correct word. You get it? So that is how the autocorrect, it does edit operations to come up with a lot of words, and with the probability of the words, it helps us to know what is the most likely candidate for the misspelled word. Okay, so now let's implement our last edit operation, which is the insert. Okay, and so the insert also takes a word, and what's going to happen is we will need our letters again, because it is letters that we will insert. So string.ascii lowercase, and it's going to return L plus C plus R for L, R in split. So we called the split function in every edit operation for C in letters. So this one is basically for every character in the English alphabet, it is going to take the left component of the word, insert one English alphabet there, and it will append the right component. This is, I mean, the simplest one you can think of, and we should have implemented this first, but I missed my ordering because I didn't check my notes that I wrote above the notebook. Okay, great. So now let's see what happens when we do inserts. Okay, so we do print insert trash. Let's insert some things into trash and see what it comes up with. So you see that we have a trash, 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 the trash, a trash, trash, trash. You see, you might not, if you are not observant, you might not see the difference between the replace and the insert. But you can see that the replace basically takes the T and replaces it with an alphabet, and it does that for all the characters in the word. But for insert, it actually start by putting the English alphabet in between things. I mean, in between the left and right components. Okay. All right. So now we have implemented all the edit operations that we spoke of over here. The next thing we want to do is, this session we're also talking about edit distance. So we need to find a way to get all the words that are one edit distance away from the misspelled word. And we also work with all the words that are two edit distances away from the misspelled word. On your own, you can implement even 3 edit distance, but what it means, like for us using one edit distance 1 and edit distance 2, is that if your word is misspelled to the point that you need more than 2 editings to get a correct word, then our autocorrect will not work. But like I'm explaining to you, you can improve it, you can increase it to even 5 edit distance. But I mean, if you misspell a word such that you need 5 editings to get it correct, then you have really misspelled it. For most of the applications, we are off by 1 character or 2. That is why I'm limiting myself to 2. But feel free, if you want to even go to 20 edit distances, hey, try it out. Okay, all right. So I'm going to create a function that is able to get me all the words. I don't want to call them words here because they are not valid words yet. Like something like B trash that we can see here is not a valid word, but we want all the candidates here. I'm going to use the word candidate. We want all the candidates that are possible words that are generated by editing the misspelled word just once. Okay, so I will say def I'll call this level 1 edit for a word. So given a word, I want all the set of candidates that can be formed by applying all the edit operations that we have defined. And because 2 different edit operations can generate the same candidate, we want to return this as a set, so that if, let's say, something is generated by the insert and is also generated by replace, which is possible, then we don't want to include them twice. That is why we are returning a set. So I'll say return a set and then call delete on the word. So we are coming up with all the possible candidates that we can form by performing the delete operation on the word. Let's do swap on the word. Let's add replace on the word. Let's add insert on the word. And this is what we are looking for. So let's try. What do we get by performing level 1 edit on trash? Okay, so print, and I'm going to call level 1 edit on trash. And I'm using trash because everything we are doing here is trash until we have actually written the function that will autocorrect for us. So you can see that if we perform edit 1, if we perform, yes, edit level 1 operation on the word trash, we get all these guys here which do not look like words. Okay, you can run it several times and it's still going to return you the same set of items that you are thinking of. So we perform the delete, we perform the swap, we perform the replace, all of them on the word itself. Okay, all right. Now let's go on to also get all the level 2 candidates that we can get. So let's implement level 2 edit on word. And over here, because level 2 is just performing level 1 edit twice, I'm going to use list comprehension. Okay, so I'm going to say return a set of edit 2 for edit 1 in level 1 edit on the word for every level 2 in the level 1 edits on whatever has been edited again. So on E1, yes. So what I'm doing here is I'm performing level 1 editing twice. What I'm doing here is just a set comprehension, but it's performing level 1 editing twice, and then that gives us the level 2 edits. Okay, so let's come here and see what level 2 edit on trash gives us. So let's print level 2 edit on trash. Okay, so you can see that the level 2 edit on trash is also returning something. Tosa, Praso, all these are not words, but in there are correct words, and I'll show you how you filter all these trash out, and then you get the correct words that are valid as far as the vocabulary for our autocorrect is concerned. Okay, so now we have implemented everything we need to implement. Let's write a function that, given a word, a vocabulary, and word probabilities, it is going to come up with what it thinks is the correct spelling for the misspelled word. Okay, so let's define a function and let's call it correct spelling, or maybe, yes, let's say correct spelling. So you give it a word, we give it a vocabulary, we give it word probabilities. Okay, the first thing we want to do is, if the word that was given to it is already in the vocabulary, then it is not a misspelled word. That is how we identify misspelled words. Remember from the explanation up here, I said identifying a misspelled word. A word is misspelled if it is not found in the vocabulary of the corpus of text the autocorrect is working with. So as long as you give it a word that it knows about, which is a word that is in the vocabulary, then it is not misspelled. So if the word is in the vocabulary, then I'm going to print that that word is already correctly spelled, and we will return. So word is already correctly spelled, or spelled, whichever one you want to use. And then I'm going to return. Okay, otherwise we need to get our suggestions. So we get our suggestions by getting all the level 1 edits. So I'm going to call level 1 edit. So we get all the level 1 edits. We get all the level 1 edits on the word, or we get all the level 2 edits on the word, or just a list of the word itself. Okay, so what are we doing here? What is it with this or? Why are we even calling or on set? If you know very much about, sorry, this is supposed to be or. If you know your conditional operators in Python very well, you remember that they have shortcuts. So if you find the or between the left and the right, because the or is true when any of them is true, if it evaluates this and is true, it will not come to evaluate the what is here. Okay, so we are doing the or to take a shortcut, so that if there are good suggestions in level 1, then it is going to not evaluate the remaining. So we have our suggestions. Now, how do we come by the best guesses? Out of the suggestions, you can see that there are a lot of, things that are not correct words in here. So the way we do that is, for every word in the suggestion, we'll filter out only ones that are in our vocabulary. Because if I'm misspelling something and you come up with something that is on my vocabulary, it's like you're even misspelling it the more. But if you're able to identify the misspelled word and you come up with words that are made out of the candidates we got from all the edit operations, we still need to filter and make sure that the words that we are going to suggest must be in our vocabulary set. Okay, so that is what we are going to do here. So I'll say best guesses is equal to word for word in suggestions if word in vocabulary. So we are only going to include all the suggestions that are found in the vocabulary. That is basically what is going on here. And then now we want to return each of the words in the best guesses and their corresponding probabilities, so that we get a tuple, a list of tuples with a word and its probability of being found. Then, depending on how we want to use it, we can either show all the suggestions in the order of the probabilities, or we can just choose the suggestion with the highest probability and use it there. So we say we return a list of tuples comprising of word and word probabilities, of that word for every word in best guesses. Yes. So let's do this and let's try out something. Okay, let's try out something. So I'm going to create a word. I'm going to intentionally misspell the word family. Okay, and then let's call the guesses. Guesses is equal to correct spelling. So we are going to give the correct, we call the correct spelling function. We give it the misspelled word, and we also need a vocab, which is known as vocabs. Mind you, we did this up here when yeah, we have our vocabs here, and we also have our word proverbs here. So we're going to pass our word probabilities here as well. Okay, now let's print what we get for our guesses. So guesses, let's print what we get for our guesses, and let's see. Suggestions is not defined, so I use suggestion here and I use suggestions here, so I need to change one of them to S. Let's see what happens. Great. So you can see that I misspelled the word family and it suggested farming or family. At this point, we are not taking into account the order of the word probabilities, but obviously you can see that the probability for family is much bigger than the probability of farming. So our autocorrect thinks that after seeing famile and looking at the corpus of text that we use to train it, it thinks that family is the correct word we wanted to spell. If it isn't family that we wanted to spell, then the next thing is farming. So you can see that on your mobile phone keyboards, when you are typing, your keyboard actually suggests to you certain words which you can readily click on to save yourself the typing. And that is a language model that is actually predicting your next words. And it also learns that from a corpus of text that you use to train it. But the logic here is similar. So it's looking at the probability of that word being found in the corpus and being the correct thing you want to substitute for the misspelled word. Let's play some more with this. So let's say I try to spell Jesus and I ignore the E. Let's see what it comes up with. Well, it appears that there aren't much words in our vocabulary that looks this way. So it is very sure that Jesus is what I wanted to spell. Okay, let's see if I spell, let's say Africa, I spell it as Africa. Let's see what happens. Well, it says Africa. Great. Let's say I put in a word like what can we try? Let's say I spell food. I spell it wrongly. Okay, great. So now it is interesting. It is thinking that in place of food, we can put either load, fund, foam, ford, road, food over here. So you can see that it still finds them, and then it is now on us, even fold, fad. You can see that all the words that it is returning to us are actually correct words which can be substituted in place of this wrong spelling. And so we have a list of tuples of suggested correct spellings and their corresponding probabilities. And now it is on us to choose which one we want to show. And this, ladies and gentlemen, is a very simple way to implement an autocorrect solution with Python. We didn't have to do deep learning. We didn't have to do, sometimes easy solutions work even better than the complex stuff we build with deep networks. But what makes this beautiful is that you don't need to know a lot of things. Just Python, list comprehension, basic probabilities, and an understanding of how this works. I agree with you, this notebook looks dirty, it doesn't look clean, but I had to do it this way so that you understand each step along the way. But like I always do, and like I promised, I like to teach you how to do AI and how to also do it well by writing clean code. So let's implement this the object-oriented way, like I've always been doing with you, and that should be enough for us to end this video. So let's get started. Now I'm not going to do a lot of explanations because most of the things have been explained. So spell checker, inherit from object, let's def underscore underscore init underscore underscore self, and we take our corpus file path, so the file path to the test file we want to learn from, and we repeat how we implemented the read corpus function. So with open corpus file path for reading, for reading as file, we come in here and say lines is equal to file.read lines, and we initialize our empty words array. So I'm just putting together all the things we did in the different cells. They are dirty, but now we are cleaning it up. So for line, in lines, I will say words plus is equal to re.find all w plus to get me all the words, and then the line to lowercase. Okay, so having created, having read this, I want to say self.vocabs is equal to set words because we are interested in the unique ones, and I'll say self.word counts is equal to counter, and we pass it words, and I'll say total words is equal to float. You have seen this code sum, and then we are going to say self.word count dot values. Okay, so we are getting our total so that we can do our probability. So self.word probas is equal to word mapping to self.word count for that particular word divided by total words for every word in self.words, sorry, in our vocabs, because otherwise it will repeat. So self.vocabs. Okay, so now I've created a spell checker. You can create an instance, and you can pass it a file. In fact, let's play with this and see. So I'm going to call, I'm going to create an instance. I'm going to call it checker is equal to spell checker, and I'm going to pass it my file bake.txt. Let's run this and see if everything is okay. All right, so great, it passes it. All right, now let's come down here and define our level 1 edit. So all the editing will be done in the level 1 edit, and then if you want to do level 2 or 3, you just repeat level 1 several times. It is much cleaner to code that way than I did in the notebook. So def, I'm going to try to make it a hidden function. I mean, Python will not enforce that, but in the community, people will know that this, I want it to be a private function. So level 1 edit, you give it a word, and what happens here is, first of all, we need the English letters. So I'm going to say string.ASCII letters lowercase. Yeah, and then I'll say my split is equal to this code you have also seen before. So word all the way to I, and word I all the way to the end, and then we repeat it for I in range len of word plus 1. Okay, so now we've done our splitting, and we are going to implement the delete, the swap, the replace, and we're going to call it all together. Okay, so I have my delete is equal to the left side plus the right. All these you have seen, so I'm not going to explain them. So left, right, for, in fact, I should be able to copy and paste these. Left, right, in split if r. Okay, I think to save myself, I'm going to copy and paste the implementation of these so that I don't have to type them again. So I have the swap, I have done the delete. No, I have the split, I have done the delete. I want the swap. So I come in here, copy swap, and over here I'm going to say swaps is equal to this. And instead of calling the split function, we've already calculated our split here. So I'm going to copy split and put it here. And that should work. Let's go copy replaces. So I'm looking for replaces. Okay, so replaces, that's this. I copy it. I come here and I do replaces is equal to this. And once again, I have to not call the split function because we have already calculated it up. And so I only call the list that the split operation returns, and this should also work. And the last thing I want to do is insert. So let me look for the implementation of the insert operation. So this is how the insert operation was implemented. So I come in here and I say insert is equal to this, and I replace split word with splits. Alrighty then. Okay, so now what we need to do is to return a set that contains all these operations. So it contains delete, it contains delete, it contains swaps, it contains replaces, it contains all the candidates from insets. All right, now let's come and implement our level 2 edits, which is just a repetition of level 1. Am I doing this on the right line? Okay, def level 2 edit self word. And so what I'm going to do here is I'm going to return a set of E2 for E1 in self dot level 1 edit on the original word itself, and then for each level 1 edit as E2 in self dot level 1 edit on whatever was in the first level 1 edit. So basically I ran level 1 edit twice to come up with my candidate for level 2 corrections. Okay, and now let's build our function, which we call check. This function is going to be responsible for checking and returning its suggestions for whatever we wanted to spell correctly. So I'll say def check self, and I'll say word, okay, and then I'll say candidate is equal to self dot level 1 edit on word, or self dot level 2 edit on word, or the word itself, so that we know if the word is already existing in the vocabulary set. Okay, so we have this, and then I'm going to say my valid candidates are just the candidate that are in my vocabulary. So I'll say word for word in candidate, candidate if the word is in self.vocabs. So if a word is found in the vocab, if a candidate is found in the vocab, then it becomes a valid candidate. Okay, so now we are going to sort the valid candidate based on probability, and that should be the end of this. So I'm going to return sorted. This is a built-in Python function, and I'm using list comprehension here. So for each candidate, and no, I'm going to return a tuple of each candidate and its word probability. So word probas for that candidate. Okay, so for candidate in valid candidate. I wish this notebook IntelliSense can help me more than it is currently doing. And the key is lambda. So I want to filter this based on the probabilities. And you see over here I'm returning a list of tuples. Okay, so the sorted is going to be called on that list of tuples returned. This is the beauty of Python. You can combine a lot of lines of code into one line, and that is why you need to learn things properly. So sorted, and it's returning a tuple. The item of the tuple at index 1 is the probability, and that is how I want to sort my items. So I'm going to sort by the first index, and I'm going to reverse it because I want the top to be the biggest. So hopefully this code is correct. And now we have an instance of checker. So we have an instance of checker. Let's create a word. Let's say misspelled word, misspelled word. Let's try to misspell the word sentence. So instead of C, I'm going to put an S. And let's print checker.check misspelled word. Okay, so let's see what comes out of it. Voila! So it saw that we were trying to spell sentence, and instead of the C, we made it an S. What if I do this? Let's see what happens. So this is why I said if you want it to be able to fix even more misspelled words, then you have to maybe go to candidate from the third editing. I just stopped at 2, and so it's not always going to work for anything that requires more than 2 editing for it to work. Let's see if we can misspell artificial. So I'm going to leave the F, and then I'll say artificial. Let's see if it's going to find it. Great. So it found out that we wanted to spell artificial and we left out the F, so it tells us that it is artificial instead of artificial. So ladies and gentlemen, this has been a long video, but I am sure it has been an exciting one as well, and you have learned a lot. These are very simple things we can do with even the regular Python we know without even delving into deep learning. And I intentionally took this detour because I feel we've learned a lot up until this point, but we want to work on an end-to-end project that will let us feel good. It will boost your confidence, and you'll be happy that you've been able to implement something that has a real world use case. So if you like this video, kindly subscribe. If you have not subscribed, kindly like the video, leave your comment there, share it with your friends, and also click on the notify button so that you get notifications whenever I post new videos. Thank you very much for watching, and I will see you in the next video. Bye bye for now.